Hello everyone, welcome to a new episode of Dive into C++ 14. In this tutorial, we're going to cover a very important topic, which is safe resource management. We're going to implement our own generic unique resource class that you can use with your own user-defined types, and the semantics of this class will be pretty much equivalent to the ones of Std uniquePointer. In the end, we're also going to implement a simple scope guard. So let's begin by defining what a resource is and why do we actually need to manage it. From Wikipedia, a resource or system resource is any physical or virtual component of limited availability within a computer system. Virtual system resources include files, network connections, and memory areas. Some real-life examples that I can think of are files, sockets, heap-allocated memory locations, and resources in games and simulations, such as models, sounds, or textures. All resources have something in common. They need to be acquired, then we can use them, and then they need to be released. Since resources are limited, we actually need to carefully think about their acquisition and release, and we need to make sure that we do not leak resources, and that means forgetting to release them. And we also want to optimize the time in which the resources are held by the system and release them as soon as possible. In other words, we need to think about the ownership of the resource and its lifetime. Fortunately, thanks to modern C++, we can actually define a generic abstraction that will wrap ownership and lifetime semantics for us without having to re-implement them every time for every single user-defined type. As you've already seen in previous episodes, heap-allocated memory can actually be managed automatically by using uniquePointer and sharePointer. And this is a simple example. We have a struct called resource. When the struct is constructed, we print acquire, and when it is destroyed, we print release. In this example here, we first define an empty resource handle using Std uniquePointer, and when Std uniquePointer is default constructed, it will hold a null pointer. Afterwards, we acquire the resource by using Std makeUnique and assigning the result of this function call to the uniquePointer. And now that we have a pointer storing a resource, we can actually transfer ownership by using an explicit std move here. So after this std move call inside of the uPointer1 constructor, the new owner will be uPointer1, while uPointer0 will again hold a null pointer. When we reach the end of the function, which is actually a scope, the resource will be released automatically, so we have no risk of leaking the resource. The sharePointer has different semantics because there can be more than one single owner at a specific time. In this case, we can have any amount of owners, and the resource will only be released when all of the owners are dead. So in this example, I have an external sharePointer here, which is outside this inner scope. I actually acquired the resource inside of the inner scope using std makesShared, and I share ownership by copying the sPointer0 variable to sPointer1 and sPointer2, and also to the external sharePointer. After I leave this scope here, these three sharePointers will no longer hold ownership of the resource, but external sPointer will, and only after I leave the scope of the function, all ownerships will be lost and the resource will be finally released. As you can see, C++11 smart pointers are really useful and safe, and they should always be used when dealing with memory allocation. What we're actually going to do in this tutorial is figure out how Std uniquePointer is implemented, and we're going to generalize it to hold any type of resource. So let's jump onto the second code segment, and first things first, we need to define some possible resource types that we're going to use with our own wrapper later. I will use a namespace called legacy to hold all the resource types, and I call it legacy because many legacy APIs have some kind of functions that acquire and release resources, and we're going to emulate that. So the most simple idea of a resource that I can think of is a heap-allocated pointer, and what I'm going to do here is just create a function to acquire a heap-allocated memory location and to release it, and what these functions will do is simply take a pointer and return it, and we expect obviously that the pointer was allocated using new, and the delete function will just call delete on the pointer. We're gonna print something if the pointer was not null, otherwise we will do nothing. Another example that I've encountered during my game development hobby is dealing with OpenGL's vertex buffer objects. So VBOs are objects used to buffer and send vertex data to the GPU, and they need to be acquired and released using specific OpenGL global functions, which have different signature because they actually mutate the passed handle pointer. We need to define some type aliases so that we can actually write the same signature as OpenGL. And the acquired function is called GL_gen_buffers. It will take an n parameter, which is the number of the buffers, and a pointer, which will be actually modified from the function. So it's like an out reference pointer. And we create a fake implementation of the function here that will print something that indicates our n parameter and the fake ID that we're using. And we're going to set the pointer to that fake ID and increment it later. As you can see, the ID is static so that we can see an example of different VBOs being instantiated. The delete function is very similar to the pointer one. If the pointer is 0, it will do nothing. Otherwise, it will print something that simulates freeing the buffer memory from the GPU. Another simple example is a file resource handle. Some APIs, legacy APIs, might return a non-pointer object such as an int to track a specific resource. So I'm going to create a fake file management API with these semantics. The open file function is our acquiring function, and it will just return an int. And the implementation is similar to the VBO one. While the close file function will check if the ID is like a sentinel or null value. In this case, I chose -1. And if it is that value, it will do nothing. Otherwise, it will simulate closing the file resource by printing something to std out. As you can see from these fake resources APIs, there is a pattern. Every resource has a function to be acquired, a function to be released. There's a specific handle type that we can use to track the resource, and there's also a null handle value that can be safely deleted multiple times. So we actually need to abstract these common features into types that we can be used as template parameters for our generic resource type. And the name I chose for this kind of pattern is called behavior. And what I'm going to do is create a namespace called behavior, and inside it I'm going to create some structs that will contain these functions, which are common to every single resource type. Let's begin by defining the freeStoreB class, which is the freeStore pointer behavior. This will actually be templatized with the type T, as we need to choose at compile time what kind of pointer we need to instantiate. And the null handle is simply null pointer. The handle type is T star. And the acquire function, which will be called init to prevent name clashes with the unique resource implementation, will simply take a pointer and call the legacy function and return its return value. And the dinit function, which will release the resource, will simply take a const reference to an handle type, and it will call freeStore delete from the legacy namespace. Our VBO behavior will handle VBO resources. The struct called VBO handle will be our handle type, and here we actually have to define a separate struct because we need to keep track of the n parameter, as we need it to correctly delete the memory from the GPU. This is a possible approach because we're storing the n parameter at runtime inside of the handle. Another possible approach would be setting the n parameter as a template parameter here in the VBO behavior, and this is obviously only possible if you know that value at compile time. The null handle here will just return a VBO handle with 0 and 0, and that's our special value. The init function will take an n parameter. It will create an handle type instance called result. It will call the legacy function, passing the ID inside of the handle as an address so that it can be modified by the legacy function, and it will set the n parameter here so that we can actually delete the data from the GPU correctly. and the dinit function will take a const reference to the handle type, and we'll just call the legacy function, passing the end parameter and the ID. The file behavior will use int as our handle type. The null handle will be -1, as demonstrated earlier in the legacy namespace, while the init function will just call the open file legacy function, and the dinit function will just call the close file legacy function. And that's pretty much it. What I'll do now is simulate our desired uniqueness semantics by simulating the management of a file resource. The first thing we do is instantiate the behavior b, and we create a new handle by using b.init. So at the moment, h0 is the only current owner of the resource. Here we can use h0 safely. Afterwards, we decide to transfer the ownership from h0 to h1, and what we do is simply create another handle and assign it to the previous one, and set the previous one to the null handle. This is called ownership transfer, and this will be done in a single operation when we actually implement our own generic ownership wrapper. Here we can use h1, but we cannot use h0 as it's null now. So, okay, h0 is a null handle. We can call the init on it, and nothing wrong will happen because our dinit function needs to support deletion of null handles. We can still use h1 here. Afterwards, when we reach the end of the scope, the resource will be released. In this case, we're simulating the release by calling dinit and setting the handle to null manually, but this will be done automatically when we define our wrapper. If we run this piece of code, this will be printed to the console. As you can see, we only have one call to open file and one call to close file, even though we transferred ownership between handles. And this is the semantics and behavior that we want our wrapper to have. In the next code segment, we'll actually implement the wrapper. So, legacy is untouched here. We do not have anything to change. We can simply go down to the new namespace called resource. And here you can see the forward declaration of our class that's called unique. And it will take a template parameter, which will be the behavior that the unique wrapper will use to handle the resource. We're doing something interesting here because we are not storing the behavior inside of the unique class. And this is actually a very well-known optimization called the empty base optimization, as this allows the compiler to not have to increment the size of the unique class if tBehavior is 0-sized. And this is very probably always the case, as behavior is just a set of functions that satisfy the resource pattern. And by using inheritance, we can avoid an unnecessary memory overhead. If you want to read more about this optimization, just follow these links here. CPP reference has a very good explanation. Our goal is to follow uniquePointer's interface as closely as possible. First, we'll define some useful type aliases here that will be used often in the implementation of the methods. As you can see, the unique resource class has to hold an instance of the handle type. For convenience and readability, we'll also define some methods that will cast the this pointer to tBehavior. This is done because tBehavior is our base class, and we want to access cleanly the methods inside of it. So we'll just call asBehavior dot and the name of the method inside behavior. The interface for the unique wrapper is pretty simple. We obviously have a default constructor that will initialize handle with a null handle. The destructor will take care of releasing the resource. We do not want to share ownership, so we need to prevent copies by using =delete. Also, we may want to create a unique resource from an existing handle, and this can be done using an explicit constructor that will actually help prevent implicit and possibly dangerous conversions. To transfer ownership, we will use move operation, so we need to define a move constructor here and a move operator equals here. Then, again, following Std uniquePointer's interface, we'll define a release method that will not call the dinit function inside tBehavior. it will simply stop the current unique resource instance from being the owner of the current handle and return the handle. This is done if you want to manually take over the ownership of the handle. We'll also define two overloads of the reset method. These methods will actually call the init. Calling reset with no arguments will replace the current handle with a null one and will actually de-init the previous one. Calling reset with a const reference to another handle will replace the current handle with the provided one. We'll also need to define our own swap implementation that will simply swap the handles between two unique resource instances. Get will return the current handle without changing it. As you can see, this is const. We'll also implement an explicit bool conversion operator that will allow us to conveniently check if the handle is null or not. And we need to implement equality operators and a global swap operator, and we're going to define them as friends because they're going to access private member of the unique resources class. One missing piece of the unique pointer interface is the Std Hash Specialization, which is often used in hash-based containers like std unorder map. We're not going to implement it just to make the code simpler. One possible approach would be like defining an hash function inside every behavior type so that every behavior implementation can implement its own hashing function. We can now start defining the previously declared methods. This is the hasBehavior conversion here, which is a simple static cast from this pointer, the referenced, to the behavior type, so that we can access cleanly the methods of behavior type. The default constructor, which is here, will simply construct the handle with a null handle from the behavior. And as you can see, this is very clean because we say as behavior instead of explicitly casting here. Upon destruction, we will call reset, and reset will take care of deinitializing the resource. When constructing from a const handle type reference, all we need to do is construct our member handle from the past one. Now for the move operations. The move constructor will copy the right-hand side handle inside of our member handle, and very importantly, we need to release the right-hand side's handle. Release, as you may remember, simply sets the handle to null without deinitializing it from the behavior. So we're simply saying, give me your handle, and you will not be the owner of the resource anymore. The operator equals move operation is similar as well, but we may be holding ownership to some resource, so we need to call reset first. After calling reset and deinitializing any possible resource, we can actually set our own handle to the right-hand side handle and call release on the right-hand side unique instance. The release implementation is very simple. We store the current handle in a temp variable. We set the handle inside our unique instance to a null handle, and then we return the previous one. The reset implementation is simple as well. We simply call the init and then set our own handle to null handle. If we're resetting, passing a const handle type here, reference, we will need to de-init the current handle, and instead of setting our own handle to null, we will be simply setting it to the past handle. All we need to do to swap two unique resource instances is swap their handles. One thing to take notice of is that we're saying using std swap here. This is to enable correct ADL lookup. And you can find more information about this topic either on CPP reference here or on this Stack Overflow question. The get method will simply return the handle. The bool explicit operator will return whether or not the handle is equal to the null handle. And these are the global functions that were marked as friend. And to check equality, we simply check equality between the handles. To check inequality, we call the equality method and we reverse its return value. And to swap two unique resource instances, we call the member swap function. That's it for the implementation of our unique resource. Now let's compare the output between our simulate unique ownership function that you've seen in the previous code segment and the real unique ownership function that will use our unique resource that we just implemented. So this line of code here, which instantiates the behavior and calls init, will be automatically done by simply instantiating the resource and passing the file behavior as a template parameter. We need to initialize the handle inside of the resource, so we actually need to pass the output of legacy open file to the resource instance. And now we can use h0 here. To transfer ownership, as you may recall, here we had to explicitly set the previous handle to null, while here by using std move and triggering the move operation, it will be automatically set as null. And we can use h1 here. To release the resource, we had to call dinit here and set h1 to null for safety. And everything here is done automatically thanks to the destructor of resource. If we run this piece of code, you will see the same output. We open a file and close a file. We open a file and close a file. And I have a really good news. I've actually tested the assembly generation with the O3 optimization, and it is identical for both functions, for both the simulated and the real one, for both G++ and Clang++. So this is a textbook example of a cost-free abstraction. We achieved safety, readability, and convenience without any runtime or memory overhead. In the next code segment, we'll take a look at some extra example, and we'll implement a scope guard using uniqueness semantics. We'll start by defining again a resource struct that will print something on construction or destruction. And then we'll test our free store pointer versus std unique pointer. The my behavior type alias will be the behavior of free store b using resource as a template parameter, and my resource will be a resource using that behavior. Statically asserting that the size of my resource is same to the size of a unique pointer of resource is a good way to check if we have any memory overhead, and in this case we don't. Now let's try using my resource and std unique pointer. In my resource, we need to call init from my behavior with a new resource, and then we can transfer ownership, and we expect this output here, which is acquire, the calls to the legacy function, and release. For unique pointer, we again need to explicitly call new or use std make unique, and we get the expected output, which is acquire and release. Again, the generated assembly is the same for both G++ and Clang++ using the O3 optimization. Some possible improvements to our interface when dealing with pointers is creating a make unique resource, taking t behavior as a template parameter here, variadic function, and also use sfine to enable some kind of pointer propagation for the star and arrow operators so that we can actually access the data inside pointer-like types more conveniently. Next, let's try out our VBO. Again, we define my behavior and my resource type aliases for convenience. And what we need to do is call init from the behavior class, and it gets us the expected output, which is GL gen buffers and GL delete buffers. As you can see, the ID returned by gen buffers is the ID that we pass to the legacy delete buffers function. There is another way of dealing with uniqueness semantics when talking about scopes, and there is a concept called scope guards, which is a feature in some languages like D that allows users to conveniently write a piece of code anywhere in a scope, which will be executed only at the end of the scope. And if there are multiple scope guards inside of a scope, they will be executed in reverse order. It does sound familiar. We can actually implement scope guards as a unique resource. So our behavior will have an handle type, which is a void function pointer, and this function has to take 0 arguments. A more efficient implementation of scope guards will probably use a template parameter to avoid the memory overhead of storing a void pointer. And you can also check out this paper here for a scope guard and generic RAAI wrapper proposal. And to continue with our scope guard behavior, the null handle will return a null function pointer. The init method will return a handle type which will be initialized by the user passed function pointer, while the deinit method will take a const reference to a handle, which is a function pointer, and just call it. We will need a helper function called makeScopeGuard here that will take a template parameter called tfunction, and this will very probably be a lambda, and it will instantiate a unique resource using scopeguard behavior by passing the ft function here. If a lambda is captureless and doesn't take any argument, it can be implicitly converted to a void function pointer, and that's what we're aiming for. And as you can see in this example here, we instantiate S0, S1, and S2 as scope guards. The second one will print B, and the third one will print C. And if we run this function, our output will be CBA, because they will be executed in reverse order. If we want to have the ABC order, we need to explicitly write the scopes here. In this case, we have the innermost scope, which holds S0, the scope here, which holds S0 and S1, and the outer scope will hold S2. And in this case, we get ABC as our output. They are a little cumbersome to use in the current form because we need to specify a unique variable name and called makeScopeGuard for every piece of code that we want to be executed. We can actually define a macro called scopeguard that will automatically generate a unique variable name for us and add the empty capture list for the lambda here. And we do that by concatenating an unlikely prefix for our variable name with the current line number. And this will be a variable of type auto. And we construct that variable using the makeScopeGuard function by explicitly saying that we are not capturing anything and passing the variadic arguments that we are using in the macro inside of the makeScopeGuard call. The variadic arguments will actually be the body of our function. As you can see in these examples, it's much easier to read and even easier to use because you do not have to specify a unique name for every scopeguard. So as you can see, we have the same example as before, and we get CBA as our output. And here, when explicitly specifying the scopes, we get ABC as our output. So that's pretty much it for this tutorial. Thank you for watching this video. I hope you found the cover topics interesting. I think that for the next tutorial, I'm going to cover shared ownership. So we'll be able to keep our legacy and behavior namespaces, and we'll actually implement a new type of resource that can use those to implement shared ownership semantics. Check out my website for my projects and more tutorials. I'm also on Patreon now, so if you want to directly support me, I'll be very happy about it. And that's it. Thank you again for watching, and see you soon.